Okay. I think let's start it because we only have 2 hours today. On the third hour, Professor KJ told us we will have a guest, the Professor Pawlik from Poland. Okay, and there will be a demo there. So let's get started. Today I'm going to talk about detection, and this is a topic of our textbook from section 6.3. So first, let me explain. Detection, in particular face detection, is a long-standing research topic. So from this figure, you can see in 1998, face detection has been developed to generate quite good results. In this image, there are 57 human faces, and all of them are correctly detected, including false positive. And you can see the false positive is here. Okay, it's another face. So how is this algorithm was designed? Okay, it used neural network. So from this figure, you can see they create an image pyramid from high resolution to low resolution, and they use a fixed window size 20 by 20 pixels to detect every windows in the image pyramid. And once they crop a region, no matter it is face or not, it will correct the lighting and applying the histogram equalization so that they can get many patch candidates. And then they apply a neural network. It includes 3 types for the 5 by 5 and 10 by 10, and this is 20 by 5 pixels. They will be treated as the hidden unit, so that they use the multi-layer perception or the fully connected layer, another name, to generate the output. It's just either true or false in terms of 1 or -1. So it is what? A classifier. They developed a neural network-based classifier to classify whether this input image is a face or not. Okay. So what I want to emphasize, the research was did in 28 years ago, and their result looks promising. So they tested their algorithm on many different types of images, including photos, printed photos, or digitized TV images. For this one, CENS, they are TV screenshot. And some, even the deezer CCTV images, like this one, okay? And they can also detect the faces from pens or from poker cards. Okay, so it looks like good. And now we are talking about a very famous face detection algorithm. It's called the boosting-based method. So when you read our textbook, you will see this figure. So let me explain what they are. Okay. And first, I want to show you a demo. Let me launch the demo. Okay. Okay, now I use my cell phone as the extensional camera, and I launch the code from OpenCV. Okay, and right. So if there are many faces on the like this one, then the program can correctly detect those faces on the screen. Even if I use your face. Too small, sorry. Okay, so let me try my face. Okay, yeah, it's correctly detected. So it's very, if you want to use it, it's very easy. Okay, and all of the code is implemented in OpenCV. Just a piece of line, you can generate the result. Let's look. Just call the cascade classifier, then a few, I think less than 20 lines. right? So let's explain how it works. And okay, let's go back. So as you can see, the name of the class is cascade of classifier. What does cascade mean? It means a series of waterfall. And why it is called cascade? Because they designed several classifiers. So each of the 1, 2, 3, all of them are as individual classifier. So what's their property? The first classifier is the fastest one. It just needs a little computational load, but it will pass many non-phase patches. It means it generates many false positives. And the second one is slightly slower, but it is slightly accurate. It passes lesser non-phase images. And the third is the further. So it is a series or a cascade of classifiers. Why do I need to design such a cascade? Because they want to speed up the detection time. As you can see here, the accuracy is quite good, okay, but however, it is not very fast. And we will show a table in the later slide to compare their performance and speed. So they have a pioneer sanity test. Okay, so here you can see there are two lines. This is the solid line, and this is the dashed line. They all use the same number of features, 200, but they are designed in two different things. The first thing is, okay, the solid line used 10 classifier and cascade in stronger cascaded. And the dashed line is a single classifier with 200 features. So as you can see, the ROC curves, they are almost the same or very similar to each other. But the speed, the cascade line is 10 times faster than the single classifier using 200 features. So that's their purpose, to detect the face very fast. So what is their single classifier? So So they use the hard feature. What is hard? Hard is a name of a mathematician. Okay, and he developed the hard sequence in more than 100 years ago. When he developed the hard sequence, nobody knows what it is. Okay, I should say 100 years ago, there is no wavelet theory. But in recent years, 20 years ago, when people developed wavelet theories, they found, hard sequence is the simplest type of wavelet theory. So they call it hard wavelet. The shape of a hard wavelet or hard sequence is very simple. It's just a positive one consecutive with a negative one. Okay. So in the Viola and the Jones method, they use hard. So this is the hard type of feature in terms of the figure A and B. Why? It is a positive one, the white region, consecutive with a negative one, the black region. So this is the horizontal case, and this is a vertical case. And the C and D are not hard feature, because hard must be positive one, negative one. But in C, it is positive one, negative one, and a plus positive one. And even this D, this is a combination of 4 detection regions. There are even more hard-like features. So from this Wikipedia's figure, you can see they can be placed as slope, or they can be placed as a circle. So in this paper, Viola and Jones only use the type of A, B, C, D. For them, that's enough. Okay. And they need they use a method to quickly compute the feature value. It is the okay. Because why? Because if they only choose the 4 type of feature, they can compute the summation of the intensity for any location x, y, and then it is very to compute. Because if you want to compute another x, y, it is easy just to sum up the summation of the bound region. So again, they want to develop a very fast algorithm. So they choose the 4 features and use the sum of intensity to calculate very quickly. So that's the reason. If they can calculate the sum of intensity for region A, B, C, D individually, okay, or I should say put the values in memory. So if they want to get the intensity of D, well, it will be easy. It will be just the value 4 plus value 1 minus value 2 and the value 3. Okay, so they can quickly get the summation of the type A, B, C, D. Okay, now they have the algorithm to develop the classifier, but however, what they need to choose? There are many different combinations of the ABCD because of location. The A type feature can be wider or narrower, longer or short, and the same for B, C, D. So how many choices do they have? For a patch size of 25 times 25 pixels, they have more than 160K features they can choose. So the problem would be, what is the best feature they need to use among the 160K features? So they need to compile a data set. They collect 4,900 images. Okay, all then are in 24 and 24 pixels. This is a sample set of their data set. Then they can do the left-right flip augmentation to extend the 4,900 positive examples to around 9,000. And they also collect 9,500 images. All of them are cropped from non-phase images. So they have positive examples and negative examples. So they use those image set to train their classifier. Okay. So they use AdaBoost. AdaBoost is what? It is a machine learning algorithm to develop a classifier. The idea of AdaBoost is, okay, we have many choice of weak classifiers, and we have many training examples. So here you can see they have almost 20K training examples. So how to decide which classifier with what kind of weights will be the best strong classifier? So the AdaBoost propose to tune their weights. So this is example how to tune the weight. This is step 1. So they search for all possible classifier candidate, and there will be a parameter for the candidate. If they can find the best parameter for the best candidates, then it will set. For example, here they suppose they set a threshold on this value on the x2 axis. So x2, x1, they use just the value or coordinate value to create a threshold. So after this step, they will go to second step. How to go to the second step? Tune or enlarge the weight of wrongly classified examples. So here from this classifier, which is collected, which samples are correctly classified. These 3 blue circles and those 5 brown triangles, they are correctly classified. And the 2 blue circles are wrongly collected because what? Because if we set this threshold, then this is the blue classes, and this is the brown classes. So the 2 blue shapes are wrongly classified as the brown triangles. So they enlarge the weights of the 2 blue circles. And then they do again, search for all possible candidates and the best parameters. So this is just illustration. Okay, they find, oh yeah, we may try this one. Okay, this is the best case. But if they use this, there are also some examples are wrongly classified. What? For example, these 3. They use this classifier. So on the right hand side, all of them are treated as the triangle classes. But the 3 circles are wrongly classified. So in the stage 3, they enlarge the weight of the wrongly classified samples, then find another best which classified. So this is the concept of ADA boost. Okay, in their case, as we say, there are 4 different types, and in the 4 different types, there are many possible locations and the shape of the 4 types of weak classifier. So they need to, the parameters they need to find is the theta. They use the theta they set the P, and the P is just a direction to control it is greater or it is less direction. And theta is the threshold. So they brute force search all possible theta and the possible shape of the 4 types. For example, if they place the shape A here, okay, they will create a value. So if the value match this criteria, they will treat the image as yes, this is a face, or it is not a face. So it is very weak classifier for class whether this is a face or not. But however, we say there are more than 160K weak classifier. Some of them are very effective. For example, these are the 2 best effective weak classifiers they found in their paper. The first is this one. Okay, if you place a white, this is a type B. Okay, type B. If the feature is placed on the eye and the cheek region, it is very useful. Because why? Because for our eyes, because it is quite relatively darker than our cheek region. And for this second, this is type C. Yes, okay. But in the type C, you can see it is different from this image because this is white, dark, white. But here is dark, white, dark. Okay. How do I control it? The parameter P. The parameter P can flip the direction of the weak classifier. So it is very useful because why? Because for our eye region, it is usually dark, bright, and dark. Okay, so these are the 2 best weak classifier. As a result, they can find, they can try many classifier. Okay, so let's go. Now they know how to design a single classifier. So they can use the ADA boost method to create many classifier. For the first one, they choose, okay, let's see this. For the first classifier, they just use a single feature. What a single feature? This one, the best one, okay? And for the second classifier, they use 10 features. Okay, so it includes the first one, second one, and the third, fourth, and etc. So they create how many classifiers? Totally 38. And so for the first one, they use 1 feature, 10 feature, 25 features, and 25 features, and 50 features, etc. So they create the cascade of classifiers. The first one is the fastest one, okay, because it only uses a single feature. It can compute very, very quickly, but it will generate many false positives. Okay, so so this is their training samples, and they train their classifier, then apply them to the test set. Also, why do they use the NIT plus CNU frontal? Because it's a benchmark. Using this data set, they can compare their performance with existing methods. Okay, now so let's talk. The paper was published in 2004. How many days they need to train their cascade of classifier? More than 7 days. On what machine? On a state-of-the-art machine 20 years ago. Okay. So, however, because one of the authors, Viola, he was a researcher at Merck, so he can borrow or use many machines, and they train their classifier, cascade of classifier periodically. So they use a single, also say 24 hours to finish the training. So this is their statistics. So how many features do they use in total? More than 6,000 features, right? And how do they run the test? Because as we can see here, okay, they create a image pyramid because their classifier is a fixed size, 20. For this paper, it's 20 by 20, and for Viola and the Jones paper, they are 24 by 24. Okay, it is a fixed size. If it's a fixed size classifier, so they need to create from an input image, the largest one, they need to create a slightly small layer and a slightly small layer, and finally it becomes an image pyramid. And from each pyramid, they will apply their method on each 24 by 24 patch. So that is the overall test stage. So there are some parameters they need to tune. For example, from a larger resolution to a smaller resolution, what is the scaling factor? Okay. So it can be several settings. So they try. The first setting is they use okay, let me see. Okay, yeah, here. Do they want to use the largest scaling factor? If this is yes, then the first scale is 1.0. If they don't, they want to skip the first largest image and just use this one, the second one as the first stage. Then the first scale is 1.25. Okay, and another hyperparameter is the step. It means from a 24 by 24 patch to the second 24 by 24 patches, how many pixels they should use. So there are two different settings. This is 1.0, it is consecutive. This patch and then the next pixel and the next pixel and next one. And another step is 1.5 pixels. So it means what? The step or the stride will be slightly larger, and they can scan less windows. So this is the summation of the total windows they used. For the setting 1, there are 75 million patches they need to check. And for the second one, there are only 19 million patches. So you can see the there's only 4 times factors between the two settings. But however, how about their performance? So compare the two RC curves you can find. They are very highly similar to each other. So if they want to process their algorithm very, very quickly, of course, for reasonable people, they will choose setting 2. Okay. Alright, so okay here. So this is their performance compared with the existing method. So first, let's take a look at the third row, the Rowley-Baluja Canada. Okay, that is the that is the method shown in this paper. Okay, so this is the Rowley-Baluja and Canada algorithm. Okay, and so let's compare their performance. Their performance, okay, in terms, okay. Let me read. The first task here means we have a data set, the NIT plus CGU multiset, and there are more than 20 phases. If there are 65 false positive, this means what? It is not a phase, but the algorithm detects, oh, this is a phase, such like this. Okay, this is a ball, but it detects that this is a phase. So this is false positive. And for the data set, if there are 65 false positive, then how many correct or ground truth phases are detected? So they can compare this detection rate. So compare with this. For the different false detection labels, the 31, so you can see their performance is slightly better than the Rowley's method. And for different labels, 95 and the further, okay, their performance is better. Okay, so the key point is what? If their performance are similar to each other, okay, or even slightly better, who runs faster? Okay, theirs method can run 15 times faster than Rowley's method. Okay, then even 600 times faster than another method. So that is their contribution. They created a method to, of course, there was some failure case because this is their training set. All of them are upright frontal. So if you turn the orientation of head to another, exceed their limits, okay, then their algorithm won't work. So, okay, so this, as I show you, I used OpenCV's implementation. Okay, the algorithm is the same, but the models are slightly different because of what? Because the OpenCV's model was trained by Intel rather than Viola and Jones. Okay, so as you can see, this is OpenCV's setting. For the first classifier, it uses 9 features. And this is OpenCV's setting. Sorry, and okay, this is Viola and Jones paper report. Okay, the parameters are different, but the architecture or the algorithms is the same. Okay, so as you can see, this is Viola and Jones dataset. All of them are parietal frontal. Okay, but in the real world, it is not the case. So this is a wider dataset. It was published in CGU 16. They compile a very, very huge dataset containing many different types of phases. Okay, so it will become more challenging. If you want to detect, Viola and Jones algorithm won't work for phases, many phases in this dataset. So let's take a look at how large the dataset is. There are some existing phase dataset, and the largest one until their paper is around 26K. But they propose a huge, super huge. It's almost 8 times of the existing, and this is only for the test case. They have a training subset. So the total number of the wider face dataset is around 400K. So it's very amazing. And there are even more labels. So let's take a label. The typical annotation was just crop the region which contains the face, but they sometimes didn't tell whether the face is occluded or what is the label of occluded. For this is partial occluded. Okay, you can see maybe more than 70% of the area of the face. But for heavy occluded, for this one, this is heavy occluded. And this is also heavy occluded, okay? It means you can maybe only see 20% of the area of the faces. They even provide the label of a typical pose. So this is very interesting. So, for example, this one, the pose, the offset orientation is not upright frontal. And this is also a typical poses, because the face is totally upside down. Okay. So they also provide a very interesting label, means event label. So because they have many training and test images, they categorize them into different events. So for example, this is traffic. This is the most difficult, because why? There are many faces in the cars. So, and then all of the faces are very, very small. So how to detect those faces? This is a challenging problem. So so this is slightly easier because the faces are relatively larger, and this is also the faces are even larger and clear, so it will be easier to detect. So they categorized all their faces into 3 subsets: the hard subset, and the medium subset, and the easy subset, so that they can use the 3 different sets to test existing algorithms which works best and on which subset, or overall it is the best. Okay, so here, this is another, this is actually quite relatively new. As we can see, Viola and Jones' paper was published 20 years ago. And then this paper was published 4 years ago, so relatively new. It is called retina face. So what they want to emphasize is, if we say detecting a face, what do we mean? What do we want to detect? Okay, so there are several levels of detection. The first level is just use a bounding box. So how many parameters you need to label a bounding box for? What? The center of the x, y, and the width and height, just the 4 parameters. You can label a face. And if you want to label a pose, okay, you need 7 parameters, because the center of the coordinate is 2. There are 2. And the pose means what? You need to estimate its orientation. So how to estimate orientation in 3D? You need a vector of 3. So this is first vector, and you need another vertical vector. So this is another vector. So the total number of parameters are 7. So they are even difficult one. It is 5 landmarks. If you want to localize the coordinate of 2 eyes, 1 nose, and the 2 sides of the lips, you need 5 points. And every point takes 2 coordinates, the x and the y. So you need 10 parameters or numbers to describe the detected face. So this is the 68 landmarks. So you can see the landmarks around the face and the eyebrows and the nose, eyes, and the mouth. Since there are 68 landmarks, so it needs 36 parameters. So if you want to use a mask, then it depends on how large the mask you want to create. So it will be the height with height. And this is a 3D mesh. It means what? Okay, so this is a 3D mesh. there will be more than 1,000 vertex on the faces. And from the more than 1,000 vertex, you can create around 2,000 meshes or triangles. So this is the mesh 1K. So they want to estimate the mesh 1K, because if you got the mesh 1K correctly, of course you got the box correctly, and its landmark in terms of 5 or 68, all of them are can be generated. Okay. So this is their approach. They call the method the retina face because it uses the architecture of retina net. So what is retina net? This is retina net. It was a paper in ICC V17. It means it is a generic object detection method. What does it mean? It cannot only, so here, when we say face detection, we are only interested in a single class, but only face. But what is genetic object detection? It is, okay, suppose you have 20 classes and you train the detectors for the 20 classes. Your detector should be able to detect all of the 20 classes, so that's generic. But if you extend the 20 to 91 classes, okay, then your detector should detect all of the 91 classes, so it's called generic. And you can see the retina net was published in 2017, and the retina face was published in 3 years later. So what if retina net can detect the face excellently? Why do they need the retina face? Why do they need to detect the domain specific, just a single class? Okay, the reason is face. If you want to detect generic objects, you can only use the bounding box. You have no other choice, because if you dog, cat, airplane, truck, car, okay, they are all their own shapes. But so you have no other choice. But if you want to detect the face, okay, you have more feature properties to explore. For example, because it is a face, so we can create the 3D mesh to match the faces. So okay, so this is the idea. They detect not only the bounding box, but also the fine length localization, and further the 1K 3D meshes. Okay, so here let's go back. The wider face dataset is a huge, great dataset, but they only provide the bounding boxes. There is no 5 landmarks labels. So how do they do? They need to create the 5 landmark labels by themselves. So okay, they create this. They can explore some existing facial localization algorithms to create those 5 landmarks. But of course, for some low quality faces, those facial localization algorithms cannot help. Okay, so they skip it. So this is the wider faces. There's training data. There are around 200K images. They can get only 84K file length annotations. And there are some existing methods to create the 3D meshes so there are several types. First, those algorithms can create the 68 vertex, and they apply another method to convert the 68 point to generate the 135 meshes. So they show us for this type of annotations, they need even higher quality of image. So this for example, this image, the quality is not very good, so it can be used to generate the 5 landmark annotations, but it cannot be used to generate the 1K 3D mesh annotation. So as you can see the number here, they have only 22K images with 1K 3D mesh annotation. Okay, so what do they want to claim? Even though they don't have the full set of annotations, they want to claim if they develop not algorithm using not only the bounding box, but also the 2D face 5 landmark annotations, and also the 3D faces 1K meshes. They want to claim, yeah, using when they train the algorithm not only on the bounding box but also on the additional annotations, they can help to improve the accuracy of the bounding boxes case. So let's see their performance report. Yeah, this is the baseline. The baseline is the retina image, the retina net. Okay, so let's add the deformable convolution network. So let's slightly adjust it and add the cascade classifier. So the cascade is here. This is the retina net. Okay, there is just a single pass. And the cascade means when they generate the image layers, okay, they will compute the loss for the first feature maps. And the feature map will be used in the second round. So this is called the cascade. Okay, so here, this is the point. If they say this is PTS means 5 land points orientation, okay, it will slightly improve the accuracy. So here, you see easy, median, and hard. What's that? That is the 3 subsets of the wider face, this one. So we see the hard, median, and easy, okay? And then they report their result on the hard, median, and easy 3 subsets. And they found if they use the 5 land annotations, okay, the performance improved. If they introduce the 3D just the vertex loss, okay, the accuracy further improved. And if they use the mesh plus vertex, and the performance even improved. So the best case would be all additional annotations are used. And this is the color. You can see the number of the color is slightly is smaller than even the hard set, because they use a different criteria. They use the Microsoft Cocoa standard. Okay, so if you set the Microsoft standard, because it uses many, I should say, 10. Okay, I should say, we will see it later. But however, you can just think it is a stricter standard, so the number is small. But however, what they want to emphasize is using their method, they can generate the best performance even on another standard average AP. Okay, so that's the end of our face detection. And we are going to talk about the pedestrian detection. This is another subsection, okay? But however, let's take a break first. Okay, now this is not demo. This is the pedestrian detection. So let me show you. Okay, and issue. Okay. Right? Okay. Okay, so this is just what I want to show. We want to detect pedestrians from videos or images, because this is a key issue for automatic cars. Okay. So yeah. So the demo I show you, it uses a very old algorithm called HUG, histogram of orientation gradient. It was published in CPR 2005, 19 years ago. But as you can see, it still works for many cases. And this is the process from the beginning to the end. It is the key point of this paper is how to extract features. So this is the given input image. This is the feature. It is a very, very long, more than one, the dimension of the feature is more than 1020 dimensions. And it applied a linear supported vector machine. This is a conventional machine learning classifier. So when it applied the linear classifier, it means there will be many weights. The weight will be multiplied on the feature vectors. And the sum will be positive value. So this f is the positive value. And the sum will be negative values. Sum the positive values and the negative values up, you will get a final score. Okay, if the final score is greater than 0, then the classifier will think, okay, this is the positive examples. It means a pedestrian. If this is negative, then it will be thinking, oh, this is not a pedestrian. Okay, so the first step is image processing, just adjust the brightness. And then the second will be the feature extraction. So let's take a look. First, of course, they need to create a data set to train their models and to test their performance. So they use two types of data set. The first is called INRIA because Dallas and Trix are awards researchers at INRIA. INRIA is France, like Academia Sinica in France. So they compile a new data set. And this is an existing data set published in IDCV 2000. We also often call them NIT data set because it was released by authors from NIT. And compare the two data sets, you can find the NIT data pedestrians in the NIT, most of them are upright or from the back. But in the INRIA data set, there are more occlusion. For example, this is occlusion. The backpack occluded part of the pedestrian, and the brightness is more. The variation of the brightness is huger. For example, this is very bright, and this is very dark, and the background and the clothing are more complicated than the NIT set. All right. Okay. So next, they need to they extract a gradient as their feature. So what is gradient? Gradient just means if it is a continuous function, then the partial derivative for every element is the gradient. So in this case, for every point on the surface, okay, there will be a direction for the first and the second element. Okay, however, for image is not a continuous function, so they will emulate the gradient use derivatives. And there are several types of derivatives for the 1D uncentered derivatives or centered. So centered because there will be a 0 in between the -1 and the +1. And then there are even 1D cubic or the 3x3 Sobel filter and the 2x2 diagonal filter. So which kind do they need to use? In addition, there another factor. Do they need apply a Gaussian filter? Gaussian filter is a blurring filter because there will be a lot of noise in the image. Do they need to apply it? Okay, if they want to apply a Gaussian filter, so how large the blurring kernel should be? Okay, so they invested the problem by try different settings. And let's take a look of this figure. So the x-axis is the false positive per window. So the fewer, the better. And the second is the missing rate. Of course, it's also the fewer, the better. So compare among the 7 curves, the lowest one is the best result. So which is the best? It is the black dashed line. So the sigma is 0. It means what? If they don't use any Gaussian kernel, Gaussian filters, the result will be better. Okay, and also because they are dealing with color image, so how should they extract the gradient features from the color images? They should convert the color image, because there are 3 channels, into a grayscale and then extract the feature, or they should extract the gradient features from individual channels and then pick up the largest one among the 3. So there are several choices. So they found it is based on their data set. The best result comes from extract gradient feature from 3 channels separately and take the largest one of them. Okay, once they extract the gradient is the feature for every pixel. Okay. So they create a histogram of gradient. It means given a cell, okay, it is the size of the cell may be 8 by 3 or 6 by 6. It's also a hyperparameter. And from the cell, okay, this is the gradient feature they extract. So there will be the horizontal part and the vertical part. From the horizontal part and the vertical parts, they can compute the magnitude. Okay, it is you can see the strength or the intensity of the gradient, and also the orientation. Because as we can see here, there are many different directions for a gradient. So, okay, this can set several bins. For example, from 0 to 20 degrees, from 20 to 60 degrees. And then once they have the magnitude and the orientation, they can create the histogram of gradients in terms of a single cell. So this is why they call histogram of gradient. And of course, there are some factors they need to consider. Which is better, signed or unsigned gradients? That means, do you need only the 0 degree to 180 degree, or do you need a 0 degree to 360 60 degrees? So this is signed and unsigned. And how many bins do they need? So for example, there are 9 bins. So this means per 20 degrees they will bin. But is the hyperparameter better if they set more bins or less bin? Or how to compute the magnitude? Okay, here the magnitude is the L2 norm, or the sum of square, root sum of square. But there are also other norms, L1 norms, or just absolutely norm. Okay, so again, they need to study different settings. So they take a look again. This is the best set. What it means? If you use unsigned gradient and there are 9 bins, then it generated the best result. And they explain why unsigned gradient is better than signed gradient. Because in their training set, the clothing and the background are too complicated. There is no useful information for the pedestrian class. But they say if they apply the method to other classes like car, or bicycle, it will be useful. Okay, because the color of the car won't be as complicated as the human's clothing. Okay, then the next step will be the block feature. This is a single cell. Okay, they can group several cells into a block and do normalization for the block. For what purpose? Because if they only consider a single block, the intensity won't be too strong or too weak. But if they consider a block, okay, the intensity of the gradient will be normalized by its surrounding cells. Of course, there are some factors. So how large should be the cell? How large should be the block? And what is the shape of the blocks? And how to normalize the block? Again, there are several choices. So for the shape issue, there are at least two different shapes. This is a grid, okay, or it is called R region or the C hub. It means it's like a circle. And okay, so they try different again settings and they tune the hyperparameter by this is a grid search. Try different cell size 4x4 to 12 to 12, and try different block size. Use a single cell or multiple cells, 2x2 to 4x4. Okay, they found. Okay, I should say, based on their training set, they get optimized hyperparameter setting. It is 4x4 for a cell and 3x3 for a block. Okay, then they also try different normalization types, and they found okay, the L2 norm, okay, it should be the best. It works best for the training set. Okay, the final issue is, should they use how large the scanning window should they use? For example, this is a slightly larger one, 24 by 128, or a slightly smaller or even further smaller. And again, because this is a scanning window, so just like the face case, how many pixels should they shift from one scanning vector to another scanning window? It might be non-overlapping or overlapping for half of the block size or overlapping for the 3/4 of the block. Okay, as I said, so they try different settings and optimize it to their best performance. Okay. So finally, okay, now they extract the feature. Then they apply the supported vector machine. The idea of a supported vector machine is try to find the best hyperplane to separate two types of data. So as you can imagine, this is the non-pedestrian, that's just the cluster of background, something. And this is the group of positive example, the pedestrian. So the supported vector machine, they try to find the best hyperplane. It means okay, there's no equations. Okay. To separate the two groups of training data. And that is a hard margin. For softer margin supported vector, if there is no such excellent separated hyperplane exist, then it will allow some it should need to tolerate some loss, and the loss is defined as the hinge loss. It means, so this is the boundary of a supported machine. If there some training examples exceeding the boundary, then there is a hinge loss. This is a hinge loss less than 1, and this is the hinge loss. The length here is the hinge loss. Okay, so this is the equation for softer margin supported vector machine here. Okay, I just want to show something. What we want to find is the parameters of the W vector. And then the W, what is the W vector? From this equation, you can see when they use linear kernel, it means the function phi is identical function. It means it doesn't mapping the feature to any high-dimensional space. It just uses the original one. As a result, the W will be a weight vector as long as the input vector x. Okay. And there will be another hyperparameter to balance the hinge loss and the width of the margin. So, since this is the optimization problem, we can use computer to solve it. And once we solve it, we will get what? A vector of weight, W. Okay, so that's we can explain. So here, this is the input image. As we can see, they have more than 300, I think. More than 2,300 positive examples. This means a pedestrian. If they extract gradients from those 23 training examples, they will create an image like this one. What does it mean? It means from their training examples, the shape of those pedestrians, they have a pattern. This is the pattern. Means we can see there is a shape of head, the shoulder, and the legs and their feet. So, it means this is the gradient features they extract, and we will have a vector of W, the weight vector for each element in this gradient feature. Then, once they get the weight, for this is a cell, then they look for the largest value among a cell. So you see the bright pixel here means for the cell. So it is to be this, and you have the W vector. The largest value in a cell, usually there are 9 elements in a cell, according to their setting. The largest value in a cell, in the 9 cell, is how large it should be. So it is very, very large. And the largest value in this cell, it is relatively small, very close to 0. What does it mean? It means for the bright pixels, they are important region. So as you can see, and for this case, what is important region? Of course, the shape of the head and the shape of the shoulder. So this region is very important if it is a pedestrian image. And the image C means the negative value for a pedestrian. So what does it mean? It means background or non-pedestrian patches. So from here, if the classifier want to check whether this image is a pedestrian or not, it will pay its attention for this region. So what is this region? It means the center of the body. If there are some horizontal patterns, it is more likely to be a pedestrian. If there is not a horizontal or vertical pattern or certain direction of the certain specific direction at this region, it is more likely it is a background rather than a pedestrian. Alright, so after the paper was published, of course there are many the paper is very effective, but there will another research issue. It would be if there are many different pedestrian detection algorithms, and there are several, for example, 6 or 5 different data sets. For example, this is a CareTech pedestrian data set and ETH, and this is INRIA. INRIA is the one released along the hug feature. then which is the best, which is the fastest, and what is the difference among those algorithms and data set. So there is a benchmark paper. Okay, this is the paper published in PARMI in 2012. Okay, if they want to answer the questions, they need first compile a very large data set so that all existing algorithms can be fairly compared on the same data set. So they created the caretaker pedestrian data set. There are how many? More than 1 million frames. How do they create it? They use a car and use a camera in the car to capture the pedestrian. So this is the comparison among pedestrian data set until 2009. So just take a look of this. They create their data set contains around 200K pedestrians. It is much greater than any existing data set. Okay, so they also, because there are so many pedestrians, so they even created the labeling tool to check whether their pedestrians are correctly labeled. Okay, so this is the reason why I need to develop the pedestrian, because if they want to develop the automatic car, okay, their pedestrian will be the most important safety issue for the car. So they estimate, okay, so let's see, some pedestrians are closer to the car, so the image is slightly large. And the sign is far away from the car, so the image is slightly small. So they created some statistics. For example, how large of those pedestrians would be in terms of pixel height. So it's from very small, 16 pixels, to very large, more than 128 pixels. And this is the distribution. And also, so they need to estimate if, okay, the pedestrian has a distance from the car, how many seconds they have to estimate, okay, this is the pedestrian, so I need to push my brake. So if the height of the pedestrian is 80 pixels, then it means it's quite close to the car. There are only one, suppose the car runs in the speed of 55 kilometers per hour. So it is a fair speed for the urban road. There is only 1.5 seconds to finish the prediction. So that, and if the pedestrian is 30 pixel height, then it means it is smaller and farther from the car. Then they have 4 seconds to finish the prediction. Okay, because they have made more than 1 million labels, they also provided some insightful statistics. This means occlusion. Okay, let's take a look at INRIA's data set. Oh, there are occlusions, but relative not as much as the caretaker pedestrian data set. And from caretaker pedestrian data set, as you can see, okay, because they take those images from a car, so there are a lot of occlusions. So they show, okay, if this is the 4 bounding boxes and this some occlusion region, then this is only remaining visible region. So what will be the distribution? Some pedestrians will be not occluded because they are very close to a car, but some of them are partially occluded and heavily occluded. If they are occluded, then what regions of the pedestrian are occluded? Okay, they found that most of them are occluded on the upper lower half part, and there are some of them are occluded from the left or the right. And they also find an interesting thing is the aspect, the width, because let's see, if a pedestrian is walking in the peripheral side, then okay, the green bounding box means the region of the pedestrian at the moment. But when the pedestrian walk and his two legs wide away, then the bounding box will become slightly larger and then become small and becomes slightly large because we have two legs. Okay, so they need to define a standardized bounding box, the yellow one. Okay, so that they can compare existing algorithms on the same standard. Okay, let's skip. So okay, there are 16 existing methods. The first, Viola and Jones. What's Viola and Jones? Just the algorithm we see to detect our face. Of course, it can be applied for detecting pedestrian. But however, how about its performance? The performance is very, very poor. This means there are 95% missing rate. Okay. And the hub feature, that is what we see for the pedestrian detection. And it was published in CPR 04, so its performance is better than Viola and Jones, but worse than some newly published papers. And this one, okay, this is for deformable part model. We will see it later. Okay, it was not designed for pedestrian only, so its performance is even worse than the hug feature. And although it was published later than the hug feature. So okay, so when we say detection, okay, we use a detection window to scan all possible candidates. We usually will have the problem of overlapping bounding boxes. So this is a example for the overlapping bounding. So we need to use some non-maximum suppression to reduce those weaker bounding boxes. And there are several different ways to it. They can use the mean shift. Mean shift means since we have a lot of bounding boxes, let's find the cluster center of those bounding boxes. And also they are pairwise max. It means let's compare. If they are overlapped with each other, so which confident or the score is higher? What is score? Score is this. Since we have a classifier, then we will generate some score. The y is, if the y is greater than 0, we think it is a pedestrian. If y is less than 0, we think, okay, actually, it is a background. So this is score. The score is larger. We have a higher confidence. Okay, this is a pedestrian rather than a background. Okay, so yeah, so there are several ways to. Okay, so we say there are 16 methods. So they compare then under different settings. So this is the overall. Among the 16 papers, they found, okay, the poorest one is the Viola and Jones, the face detection algorithm. The reason is very clear. For our face, face is a highly structured pattern. So they found the most useful one, okay, is this pattern, bright and dark. And the second useful one is the dark, bright, and dark. Okay, because of the structure, so their highlight feature works very good. But for pedestrian, no. For a pedestrian, the shape feature, it means the hug. This one, the hug works good. Okay, but we don't have any highlight. We don't have any effective highlight feature. Although Viola and Jones method can be applied for pedestrian detection. So, okay, they compare the 16 method for. Okay, they found Viola Jones was best, and the sun works good. Okay, so they try different settings. This is the reasonable subset. It means what? Because some images are very small, less than 13 or 20 pixels. For that, it's unreasonable, too small. It's difficult for them to tell, okay, do you correctly detect it? Although we have the label. So they filter out images less than 50 pixel height and pick up the reasonable subset. However, they also found, okay, Vieira-Jones method works poorest. And if they try different occlusion cases, it means no occlusion or partially occlusion. Okay, they can also rank the performance of those methods. But however, they found they are consistent. It means for some algorithms, if they work well for one setting, it also works well for another setting. So it shows the benchmark is a good metric to measure those methods. So they also use the same metric to measure different data sets. Okay, they found this is INRIA, the data set released by the DALA. This is a Daimler data set. Daimler means Benz. Okay, this is a car manufacturer, so they are also interested in the pedestrian detection. And okay, the most challenging one is the Caltech Train and the Caltech Japan. So, however, as we said, accuracy is an important issue. But another important issue is time. They need to detect the pedestrian as fast as possible. But however, the best performance the algorithm, okay, it is this one, multi-frame plus motion. It runs very, very slow. Okay, no matter for the height greater than 100 pixel case or the reasonable case, it is the slowest one. Alright, so this is an important extension from the pedestrian detection to generic image object classification. It means deformable part model, or we can call it a path-based object model. It means for this pedestrian, okay, it detects its hug region not only for a fixed pattern. It allows some part of this model can be occurred in any region, in any place in the allowed region. So, okay, so you can see here what feature does the method use? The same hug, okay, but it creates a multi-level detection. So from an image pyramid, they can create a hug for the smallest one, slightly larger resolution, and even the largest one. So this is the low resolution hug feature, and then this is the high resolution hug feature. They extract the low resolution feature from the low resolution image, and they allow the high resolution hug feature can be deformable. Okay, so they show the positive detect rate. For this is the person. They use the Pascal VOC dataset to train their classifier. There are only 20 classes in the Pascal dataset, and one is person and another is cow. So how to detect a person? Just like both of them use hug feature. And here you can find it detects the head, the left shoulder, right shoulder, left leg, right leg, and the feet region. So the Skinner, he is not stand upright frontal. You can see the screwness of his body, but okay, because they allow the deformable of the shape, so it can still correctly detect the skinner. Here the same, okay, they detect the shape of the head of the cow, okay, the left leg, right leg, and its feet. So it detects. So since there are 20 classes in the Pascal VOC dataset, so they need to develop 20 classifiers for each of the classes. This is a button. You can see the roughly shape of the button and each detailed pieces. And this is a car. So you can see this is the shape of a car from the frontal. And however, some cars are slightly wider, some cars are slightly higher. So the deformable feature allowed then there are some changes of their shape. And this sofa and the bicycle. But let's see some interesting result. Okay, so the pedestrian, yes. Again, the pedestrian here, he is not upright frontal because you can see his body is clearly sloped. And for this, some people are standing and some people are sitting. Okay, so this is the best case because the deformable allow them to be detected even though they are not sitting. And here is a person behind the bush. The deformable part allow it to be detected even though there is only the head and the shoulder part. However, this is a wrongly detected case. This is a sheep. But if they use the pedestrian detection to detect, it will tell you, oh, there is a person. Why? Because of shape. He think, oh, this is right shoulder, left shoulder, the top of the head, and this is the leg. So, of course, no detector is perfect. This depends on how do we design it. So, for the car case, there are several cars, and all of them are correctly detected. But however, this is not a car. This is a bus. They found the same patterns. This is the wheel. This is the roof, and this is the end of a car. So it is reasonable. Although the image is wrongly detected, we know the reason. So this is the advantage for the conventional machine learning classifier. It is easy to understand. Okay, so let's talk about a very important dataset for Microsoft Cocoa. It was released in 10 years ago. Okay, why it is very important? Because it's very large, and it is the first dataset providing the instance-based segmentation labels. So what is instance-based label? If we want to detect an object, okay, we will only provide the bounding box. So there are bounding boxes for the man, for the sheep, and for the dog. And because if they provide, so this work. This work means Microsoft. They provided the segmentation labels for each of the instances. Why is it important? Because if you have the segmentation label, you can easily create the bounding box. So this is, if you have this, you can easily generate the bounding boxes. And how large the dataset is? Okay, so let's compare Microsoft Cocoa and the Pascal VOC. There are only 20 classes in Pascal VOC, but there are 91 classes in in Microsoft Cocoa. And pay attention to the scale. This is log-based axis. So this is 10,000, and this will be 100 or 10 times of 1,000. Okay, so a gap is 10 times. So take a look of this figure. So this is Pascal VOC. There are 20 classes. And how many images do they have per class? Around 1,000. And how many images do they have in Microsoft Cocoa? More than 10,000. Okay. And we see the Caltech pedestrian detection dataset already. There is a single class, just the pedestrian. However, there are a lot of images. And compare with ImageNet. ImageNet, there is also a detection subset. But however, although there are more classes, the instance per classes is close to Pascal VOC, much less than Microsoft Cocoa. So that's the reason Microsoft Cocoa is very important. And these are two example cases. For person, okay, it created the pixel labeled segmentation data, and this is for dog. Okay, and so why Microsoft Cocoa is so important? Because you can imagine how much money they need to use to hire American aeromechanical Turkers to label those images. Huge. It's very huge. Okay. So Pascal VOC. The Pascal VOC is released by Oxford University. They don't have so much money. But Microsoft, yes, it is a very rich company. If they want, they can create the dataset. Okay. Alright, so okay. As you can see, it is so large and so many categories. So when it was released in 2014, okay, it goes along the rapidly developed of neural networks. So in AlexNet, as you can see, it is the important image classification released in 2012. So in 2013, there's a fast RCNN. So the CNN just means convolutional neural network. It applied convolutional network, used AlexNet as the best form to do detection. So this is the 15 means 15% mean AP. And then VGG16 was released in 2014. Okay. Then if they use VGG to train the same detection model, the same fast RCN, because the VGG network is much more powerful than AlexNet, so it also boosts the performance of image detection. And even though they use the same backbone, they fine-tune the design of the detection algorithm. So this is a fast RCN. This is a faster RCN. The performance is even boosted. And when they use the same faster RCN but replace the backbone from VGG to ResNet, okay, the performance also boosts. So you can see best network and better detection algorithm. So year by year, from 2015 to 2018, the performance of on the ImageNet increased year by year. And what is the DPN? There's a 5% DPN. DPN is this. This is DPN. As we see, this is just a DPN. Okay. Okay, so now let's talk about how to measure the performance of detection. And we will use the IOU. It means so for a detection algorithm, it will need to decide the location. Okay, this is a region, and the confidence of a specific class. So for the location, we will use the intersection of the ground truth. So this is ground truth and the predicted region. The prediction is a dashed line. And so we will calculate the IOU value. And then we need to calculate the precision and the recall. So what is the definition of precision? It is the number of truly positive detection divided by true positive plus false positive. So what is so we know the detection region. So it means if you predict that this is a kite and you give a score, if the score greater than a threshold, or you will see, oh, there is a kite. So it is decided by the confidence threshold. And the true positive and the false positive, it depends on, okay, if there is a ground truth, how much the detected region overlapping with the ground truth. So there will be another threshold, means IOU threshold. So this is, if we want to calculate the precision, it will affected by the two factors. One is confidence threshold, another is IOU threshold. And if we want to calculate the recall is the number of ground truth positive, and dividing the number of truly positive is the predicted region. So it is affected by what? The IOU threshold. If we draw if we adjust the confidence threshold, we will get the curve in terms of a specific IOU threshold. So if you set the IOU threshold as 0.5, we will get this curve. And 0.7, we will get this curve. And 0.9, we will get this curve. Okay, you can calculate the area. So you see the y-axis is from 0 to 1. The x-axis also from 0 to 1. So you can calculate the area of this region. It is a value less than 1. The larger, the better. And there are several thresholds. If you use 0.5 to 0.95 for 10 scale, and average the 10 scale, you will get the average precision. And for Microsoft Cocoa, there are 91 classes. If you average the 91 mean of square, you will get the mean average precision. So that is the final score for a detection algorithm. Okay, so this is YOLO family. YOLO is what? It's a detection algorithm emphasizing speed rather than accuracy. So this is YOLO V2, and this is the Retina net. Okay, let's take a back to the Retina. So Retina. Okay. Yeah. So this is the Retina net. Okay, and compare with YOLO. YOLO is extremely fast, but very inaccurate. So YOLO family, there you can see 1, 2, 3, 4, 5, 6. Currently, the latest version is 9. They are developed by different companies or universities. So even you can see X means 10. It doesn't mean, okay, it is the latest one. And okay, this is the improvement of. So this is the top one is the YOLO V9. This was just released 10 months ago. Okay, and it was developed by our Taiwanese. It's released by Academia Sinica. Okay, so as you can see, the improvement for YOLO family, it emphasizes the speed. Currently, it reaches around 55%. Okay, it compared with several. This is 7 years ago. The accuracy is also 21. Now it is 55. A huge improvement. Okay, now we are going to finish our lecture today, and next course, the Professor Public is here. Okay. Hi, KJ. Yeah, we end up.
Okay.
Okay.